Welcome to Business Mathematics 2 MA 1203. I'm Eric from Mathematics Study Program, Faculty of Mathematics and Natural Sciences ITB. So for today, in this session, we will discuss about numerical integration. So specifically, we will discuss the first method for calculating integral using numerical scheme, that is the trapezoidal rule. So let's review first about what is meant by integration. So in the last semester, we remember this table of integral, and we want to find lots and lots of integral. So now we are going to find this integral. Okay, yeah. Here, yeah, this is too hard to find using the method that we have given in the last semester. But we can get the approximation of this definite integral. We can have the approximation of this definite integral. Don't forget, what do we calculate of this definite integral? What I meant by a definite integral is the integral with the upper and lower boundary. Okay, yeah? This is definite integral. When we are calculating this, we are calculating the sine area. Don't forget, the sine area. And if it is always on the upper part of the x-axis, we want to find the real area. Okay, so this is, we want to find, how do we find this approximation of this definite integral? I want to find the approximation by using by approximating the area, under this function. Okay, yeah. And we don't have in this session and in this chapter, we don't have to memorize all of this formula. You can forget about this all. So let's look at the first one, that is the trapezoidal rule, the first method for finding approximation of definite integral. So this is the trapezoid, and the length of the parallel sides is A and B, and this one, the length is height, the width is height, h. So what is the area? The area is given by a half times the height, times the summation of the parallel sides, the length of the parallel sides, that is A plus B. Okay, so let's say that I have this curve. So I have this curve. I want to approximate this by using by calculating the trapezoid of this. So this is the trapezoid of this. Yeah, this is a triangle. Yeah, this is the, from this curve, we look at the left end and the right end. The height is given by this. The height of this is given by this. I can approximate this using the red trapezoid. Don't forget, this usually have an error. The error is this one, yeah. And this one is the error. And this one is the error for the last trapezoid. Okay, don't forget this is x. So this is the height of x. So this is f. The value of f at this. So how do I get the approximation? Let's say that the height is 1, the height is 3, and the height is this 2, and the height of this is 0. So the approximation is a half times the first one. This is a triangle. A half times the height. The height is always the same because this is 1, 1, 1. A half times 1, that is a half, times A plus B, the parallel sides, 0 plus 1. What about the second one, the red one? A half times 1 times the summation of 1 plus 3. Okay, yeah? And the last one, a half times h is 1, times the value of f at this one is 3, and the value of f at this one is 2. So you have 3 plus 2. Okay, yeah, you have a half times this plus a half times this plus a half times this. You know you have a half, a half, a half. I can use distributive. So I have 1 times 0 plus 1 plus 1, that is 2 times 1, plus 3 plus 3, that is 2 times 3, plus 2, that is 1 times 2. Okay, yeah. Remember this pattern. 1, 2, 2, 1. Why do I have 2? Because when we are calculating this area plus this area plus this area, this is counted twice. So 2 times the height of at this one plus 2 times the height of this. Okay, yeah. So this is the value of f at x, the value of f at x, the value of f at x. Okay. So let's say that we want to find approximation of this. So I want to find the area under x squared, the area under x squared from interval 0 and 1, 0 to 1, using two subinterval. So I have 0 to 1. I divide it into two subinterval to make it simpler. We want to use two subinterval that have the same length. So I have 0, a half, 1. 0, 1 is divided into two subinterval, 0, a half, and a half to 1. And fx is x squared. So I can look at this using two trapezoid. Okay, yeah? Divide, okay, with the same length. Okay, so the x is 0, the first one, 0. The second one is a half, 0.5. And the third one is x1. Can you imagine the trapezoid? This is the trapezoid. The height is this maybe. The height is this. The height is this. What is the height of this? Fx0. What is fx0? F at x0. x0 is 0. So f of 0. And fx is x squared. So f0 should be 0. What about this one, the height at 0.5? F of 0.5. F of 0.5 is 0.5 squared. So you have 0.25. What about this one? F of x2. F of x2 is f of 1. F of 1 is 1 squared, so 1. So the height at 0 is 0. The height of x1 is 0.25. And the height of x2 is 1. So you can imagine the trapezoid. This is the first one. And this is the second one. Okay, you can imagine, yeah. So remember the formula of trapezoid is a half times the height times the sum of the length of the parallel sides. So if we can, this is the approximation. We can look the approximation is a half times the height. The height is is always the same because this is same length. So you have a half times this height plus this height, fx0 plus fx1. This is the same, a half times the height times the sum of the length of the parallel side, fx1 plus fx2. So I can, this is the same, a half times 0.5. I can get it out using distributive. So we have 1 plus fx1 plus fx1. That is 2 plus fx2. So I have this one. Remember the pattern. 1, 2, 1. fx0, fx1, fx2. A half times this, and I can get the approximation is this one. Pay attention to the notation. This is approximate by this, but this is the same as this. Don't forget, what do we mean by equal sign? This is equal to the row before, that is this one. So this one equals this. So this one is not approximated by this, but this is the same as this. So we usually call approximate, but this is equal. Okay, what about if we are want to using three subinterval to approximate this? Okay, yeah. So x0 should be 0, 1/3, 2/3, and 1. Do you know why? And fx0, don't forget fx is the same. Fx is still the same, that is x squared. We want to find integral of x squared from 0 to 1 using three subinterval. So you have this 1 interval, 1 interval, 1 interval. 0, 1, this divided to 3 subinterval with the same length. Okay, yeah? So by using the graph, we can have this is approximated by a half times the length. the height is always 1/3, 1/3, 1/3, but now we have 3 trapezoid. This is the length plus the length, the length plus the length, the length plus the length. I can use distributive, so I have this one, and you have 2, 2, you have look again, the pattern, 1 fx0, 2 fx1, 2 fx2 plus 2. How do I get this? Because when we are counting fx1, is counted twice, because it belongs to the first trapezoid and the second trapezoid. The same fx2, it belongs to the first, the second, and the third. So I have this one, I can use this, and I have the approximation. Okay. Okay. We will. What about if we are going to use a 4 subinterval? So x0 should be this, x1 should be this, x2 should be this, x3 should be this, x4 should be this. Try to know why do we have 1 over 4, 2 over 4, 3 over 4, and 1. Don't forget the same length. 4 subinterval from 0 to 1, from 0 to 1 is divided into 4 subinterval with the same length. So I have this one. What is the height of this? fx0, fx1, fx2, fx3, fx4. So this all is the height at this, and this. Because we want to approximate using the trapezoidal rule. And this is approximate by a half times the height. The height is always 1 over 4. You can look at this. But don't forget, this is the parallel side if fx0, fx1, fx1, fx2, fx2 plus fx3, fx, and I can use distributive law. So I have, look again, the pattern 1, 2, 2, 2, 1. And I have this one. And this is the approximation. Okay, last one. What about we want to divide it into n subinterval with the same length? Can you guess what the x1 is? And what is the length of the subinterval? Yes, the length of subinterval is 1 over n because we want to have integral 0 to 1 divided into n subinterval. So the subinterval should have the length that is 1 over n. So we know that x0 should be 0, x1 should be 0 plus 1 over n, x2 will be 0 plus 1 over n plus 1 over n, that is 2 times 1 over n, x3 should be 0 plus 1 over n plus 1 over n plus 1 over n, so it should be 3 over n. What about the last one? That is 0 plus n times 1 over n, 1 over n, 1 over n, so n times 1 over n, that is n over n, that is 1. It makes sense, isn't it? So what is the height here? fx0, fx1, fx2, and then fxn. Okay, and the integral is approximated using by a half times 1 over n times fx0 plus fx1, fx1 plus fx2, fx2 plus fx3, fx3 plus fx4, and so on. And I can see the pattern. 1, 2, 2, 2, 2, and 1. So this is the approximation. And now, what about if I want to find if the interval is 0 until 2? Okay, because we want to approximate this using 4 subinterval. Can you do this by yourself? Okay, what about this one? If I want from 1 to 3. If I want to divide by 4 subinterval, what is the length of the subinterval? From 1 until 3. The length is 2. From 1 to 3, the length is 2. I want to divide into 4 subinterval. So what is the length of the subinterval? Very good. 3 minus 1 divided by 4. That is 1 over 2. That is a half. Okay, so this should be a half, and x0 should be 1, x1 should be 1 plus a half, x2 should be 1 plus a half plus a half, so 1 plus 2 times a half, and xn should be 1 plus n times a half, and so on. If you want just only 4, so x4 is 1 plus 2 over 4 times 4, that is 3. Okay, Now, generally, so I have this one. If x0 is not 0, if a, so I have x0 is a, so this is the height, a plus b minus a divided by n. What about x2? This one plus this 2 times the height. What about xn? A plus n times the height. So this one. So I can get this. This is the height at this, the height of x1, the height at x2, and the height at xn. And generally, I have this formula. This is for approximating integral a b fx dx using n subinterval. Look again the pattern. The pattern is 1, 2, 2, 1. Okay, yeah? And notice when the number of subinterval are getting larger, the approximation is getting closer and closer to the exact value. Do you know why? Okay, yeah? How close the approximation to the exact value is what we usually call an error. We will see again the error of approximation with this method later. Okay, yeah? Next, in the next session, we will look at the second method for finding approximation of definite integral. That is the Simpson's rule. Thank you.